Hi everyone. Today we're going to be talking about a very important theorem that we use in economics. It is called the envelope theorem. Now, the envelope theorem tells us how the optimal value of a particular function changes whenever a parameter in that function changes. So, to put this in perspective, for example, in the previous lecture, I talked about the optimal value function f star, and this was a function of the constraint constant c. So that c was our parameter in that function, and we saw that when we took the derivative of the optimal value function with respect to the constraint constant, we got the Lagrangian multiplier. So this was part of the discussion where we provided an interpretation to the Lagrangian multiplier, but the kind of derivative that we took there, that is the kind of calculation that we are looking at in today's lecture. What happens to the optimal value function whenever any one of the parameters in that function changes? Okay, now to provide some details as to what I'm really getting at, we look at example 18.6, which I believe you would have tried by now. We have already posted a video on that. Example 18.6 was about choosing K and L. This was a minimization problem where you're minimizing R times K, you're minimizing your cost, R times K plus W times L, where R is the price of capital and W is the price of labor. So you're choosing K and L to minimize RK plus WL subject to producing a given level of output. So the constraint constant is that K to the power half L to the power 1/4 should be equal to a given level of output Q bar. Now here we are talking of a problem where we are dealing with three parameters: our constraint constant, which is Q bar, the price of capital, which is represented by R, and the price of labor, which is W. Okay, so these are our three parameters. And we might be interested in knowing, so if I look at my optimal value function, which in this problem would be given by R times K star plus W times L star, once I substitute the optimal values, I might be interested in knowing how the optimal value function C star changes when, for example, R changes or W changes. And that is exactly the kind of question which is being asked in example 18.6. Now in this example, our Lagrangian was Rk plus Wl plus lambda times the constraint constant Q bar minus K to the power half L to the power 1/4. You must have got your stationary point from by taking the first order partials and putting them equal to 0. So from there you got the optimal as, let's say, represented by K star and L star. And once you substitute these values into the optimal value function, which is C star, you would have got 3 times 2 to the power minus 2/3, R to the power 2/3, W to the power 1/3, Q to the power 4/3. Now the question asked you, calculate the partial of, calculate the derivative of this optimal value function with respect to the parameter R. And here when you did the calculation, so after doing calculating this, you would have found out that this expression, once you simplify it, it's nothing but the expression that you got for K star in your stationary point, as part of your stationary point or as part of your optimum. Right, so this is what we are getting at here. And similarly, if you were to calculate the partial of C star with respect to the constraint constant, let's say the price, sorry, not the constraint constant, but the price of labor, which is W, that is L star, and the partial of the optimal value function with respect to your constraint constant Q bar, that has to be nothing but your lambda, the Lagrangian multiplier. So basically, if you have actually done this problem, what I'm trying to say here is that this is a fairly long problem, and what the envelope theorem tells us is that there is a shortcut. what the envelope theorem gives us is actually a shortcut to doing exactly these same calculations. So this is what we're going to look at today. What exactly is this shortcut where we can get these partials straight in just like 1 or 2 steps? Okay, and that's what we're going to focus on in the next video.